So, we have completed the foundational introduction to statistics, and we are moving into curve fitting and dimension reduction. And we'll tackle this systematically, starting with linear curve fitting, and then nonlinear curve fitting, and then get into dimension reduction methods. And by dimension reduction, you've actually done a little bit of this already, although unwittingly, perhaps. The genetic algorithm is a method of dimension reduction because you're taking a spectrum which has 1024 dimensions and reducing it down to a single intensity on a single detector. So there, it's actually the dimension reduction is in the physical hardware. But we'll talk about methods for taking the spectrum and reducing its dimensionality to turn it into something that's a little more tractable. And the methods that we'll be focusing on primarily are principal component analysis as an untrained algorithm, and linear discriminant analysis as a trained algorithm. And so this is just two sort of representative dimension reduction methods that cover a broad swath of approaches that are out there that build off of those two general architectures. So that's the road ahead. All right. And we'll be doing some MathCAD problems on Tuesday, so plan to bring your laptop for that as well. And we'll be covering linear fitting, mostly. And that's the topic for today. All right, so when might you do linear fitting and what is this all about? The sections that I'll be chatting about today are covered in 5.1 and 5.2. And I'm going to give you the abbreviated version. But I encourage you to look through those for use those as an additional resource. Okay, so why curve fitting? Wow. That is impressive. Okay. Yeah, let's keep that. That was so fantastic. We should definitely keep that. Let's see if we try this one more time. My pen works. Hey, there we go. Okay. Wow, that's so much better, isn't it? There's got to be a way to make this thinner. Well, I'm just going to deal with it today, which means you're just going to have to deal with it today too. That classic example, y equals mx plus b, right? We've all done this, a linear fit to a data set. Why do we do the linear fit? Well, because we can, right? It provides a lot of additional information than just a single scalar value. If we have a trend, then we can test whether or not the data is consistent with an anticipated trend. So that's sort of the bottom line. I actually almost feel silly talking about why one would do a curve fit to this room, because hopefully it's obvious. But the real question is, how do we find the most probable values for the coefficients m and b? And I'm going to rewrite this as y equals a0 times x plus, a0 plus a1 times x. Because that's how we'll be evaluating it in the math. A0 and A1 are the two parameters we're looking to extract from the fit, the constant, the intercept, and the slope, respectively. All right, so how do we do this? The question we're going to start with is, what are the most probable values, given a set of y values for a given set of x values, what are the most probable values for A0 and A1? We're going to determine this by the method of maximum likelihood. supposed to be an MML. Let's be a little bit more specific in our question. If the data are normally distributed, what is the probability of observing a particular value of y? And then once we have how to do that particular value of y, what is the total probability for observing the collective set of y's? So that's the approach we're going to take. All right. So dP, the probability density for a particular y value, yi, if it's normally distributed, then this is the probability density function, right? And what is mu sub I in this case? Mu I is given by A0 plus A1 x sub I if these were the true correct values of A0 and A1. Yeah?
Is that y sub I?
Yes, it is, but my pen is not working as well as it usually is, and it's making lines thicker and not separating things as well. So that is supposed to be an I subscript and not an L.
Thank you.
Yep. Okay. So that's the probability of it's probability density, because the probability of actually observing a particular value is infinitesimally small, right? But a probability density we can still discuss. All right, so that's the probability of obtaining a particular y value. What is the probability of obtaining a collective set of y values? That's going to, it actually goes right back to the dice roll example that I brought up during many of your exams. What's the probability of rolling snake eyes? 2 ones. It's the probability of rolling 1 on one die and the probability of rolling another one on the other die multiplied. So it's 1 over 36, right? So it's the exact same idea here. The total P tot come on, do something, pen. I think the battery might be dying in it is the problem. And it takes quadruple A's. They're very hard to track down. I know. I had that very same reaction when I looked it up, pulled it out. What the hell is that? I don't know if it'll work.
Oh, the pinpointer will work. You just can't link it up Bluetooth-wise. It is the sharpest pin.
Well, I might just go back to the document cam if I can't get my computer to work too. Let's try just turning it on one more time.
Sometimes if you unscrew it and like take the battery out for a second, I know it sounds
We'll give it a shot.
But it works. It helps with mine.
It's like MathCAD. Sometimes it just has to be rebooted, right? Like every 5 minutes.
See? And it's thinner too. So.
Yeah, and I definitely do need a new battery. That's what this is also telling me. Okay. So P tot is going to be the combined product, which will be we'll write that as pi, which is a product of I. It's just like sum is given by S. P, a product of terms is given by pi. and that's going to be P sub I, right? The probability of each individual y value multiplied together is going to give you the total probability. And that's going to be for a Gaussian distribution, just substitute in a normal PDF. We can do some things to simplify this product. We can recognize that a product of we can use the commutative properties of products. In other words, the product of A times B times C equals A times B times C. So we can regroup these and turn this into the product of 1 over square root of 2 pi sigma squared times this product. What's e times a, e to the a times e to the b equal to? E to the a plus b. So I can write this as that term times e to the minus 1/2 summation of yi minus a0 minus a1 xi squared over sigma I squared. Hopefully everyone can still see that. On to the next page.
So you turn mu I into the linear form over there. What about those variance?
So the question is that I substituted in for mu here, a0 plus a1 xi, right? The question is, what do I do about the variance? And why do I even have a subscript on the variance? Is that not a constant? Is that what you're sort of getting at? Or maybe I'm misunderstanding the question.
I thought you'd have to substitute something in for the variance as well.
No, actually we're fine there.
Okay.
And in fact, I'm leaving this in the most general form where each individual measurement can have its own variance. We'll simplify when we do the next stage. I wanted to leave it this way because we're going to introduce what the definition of chi-squared, and I wanted to leave it in its most general form for that case. Ready for me to move on? Okay. So that has a special name, that summation. I'm going to rewrite this total probability in terms of that on the next page. So P tote, and actually this is, technically it's still a d P tote. A differential, but it's a probability density still. That's going to be this the product term that's still there times e to the negative 1/2 summation over I yi minus mu I squared over sigma I squared. And this, inside the brackets, we call chi-squared. let's consider explicitly the case of sigma I equals just sigma, which is another way of saying that every measurement has the same variance, which is a common fact experimentally. In that case, I can pull out the sigma, right? And I can write this as dp tot equals this term in brackets, e to the minus 1 over 2 sigma squared, summation of yi minus a0 minus a1 xi squared. Let's go blue. And now we're going to maximize the total probability with respect to A0 and A1. Right? We want to find the most probable values for A0 and A1. When will we have the most probable? When the probability is maximized. Right? If we're maximizing the total probability, this is a constant with respect to A0 and A1. So that's not going to be very interesting in terms of the maximization. Right? If I rescale the probability by a constant, I'm still maximizing to the same value. What about what about chi-squared? Turns out that because it's a negative exponent, maximizing probability corresponds to minimizing chi-squared. Yeah? Maximize total probability corresponds to minimize chi-squared. Does everyone see that? Okay, so let's go ahead and do that. How do we determine the minimum with respect to, if we want to maximize or minimize a function, how do we find that? The maximum or minimum with respect to some parameter.
Derivation.
I'm sorry?
Derivation.
Derivation. Take the derivative. And the place where the derivative is equal to 0 corresponds to the maximum and the minimum. So let's take the derivative of dp tot with respect to A0. And formally, because we're doing partials, it'll be a partial derivative of d tot with respect to A0. Actually, we're not even going to put d tot in there. We're just going to put chi-squared. Because we've just determined that those are equivalent. Minimizing chi-squared is equivalent to maximizing total probability. So if I take the derivative of chi-squared with respect to A0, then that corresponds to del A0 of the summation over I, yi minus A0 minus A1 x sub I squared. I can move the derivative inside the sum. In other words, the derivative of a sum is equal to a sum of derivatives. Should I write that down? Because I don't know if that made sense to everybody. Del x of f of x plus g of x equals del f of x del x plus del g of x del x, right? That's all I'm saying. Oh, so because of that, we can take the derivative operation and move it inside the sum instead of outside the sum. So we can say basically del chi-squared del A0. We know it's going to be equal to 0, so let's go ahead and set it equal to 0 now. But that's also going to equal the summation of, over I, the derivative with respect to A0 of yi minus A0 minus A1 xi squared. Okay, so how do we take the derivative? What is the derivative of that thing with respect to A0? No. Yes. Close. Anyone remember the chain rule? Good old chain rule. The thing I love about differentiation is it's deterministic. Integration is hard, right? Because you never know exactly what you're going to get, and you have to sort of figure it out by induction. But derivatives, there are rules. You can always figure out what the derivative of something is going to be. So we've got this squared term here. So the derivative of something squared is 2 times that thing, and then we take the derivative of whatever was inside. So the derivative with respect to A0 is going to be the summation of I of yi minus A0, 2 times that, right, minus A1 x sub I, not squared anymore, times the negative 1, which is the term in front of A, 0. Yeah? Which is equal to negative 2 summation of yi minus A0 minus A1 x sub I equals 0. Barely ran out of room there, but I can write over here, but it doesn't really help you, so I thought I'd stop in the accessible screen. So we can multiply both sides by negative 1/2, and it turns out negative 1/2 times 0 is still 0, so we can get rid of the negative 2. Right? And now let's just rewrite. This whole thing is equal to 0. We'll move everything, we'll move the A terms over to the right and leave that first summation to the left. Yeah?
What'd you do with getting rid of negative 2?
Oh, okay. I have this. We'll put it back in there for a minute. Negative 2 times this equals 0. So I multiply both sides by negative 1/2. And that gets rid of my negative 2, but the 0 is still 0. Or you can divide both sides by negative 2, if you like. Either way, you get the same thing. The point is that scalar doesn't really affect the 0 doesn't care about a constant scalar. Okay, so now if I'm going to go ahead and get rid of this now, so I don't have to, well, I shouldn't have done it that way, but well, no, I won't bother messing with it. The negative 2, I'll do it this way. Negative 2 scratched out, there. That's what I really wanted to do. Okay, so let's go ahead and rewrite that equality. That whole thing in brackets was equal to 0. I'm just going to rewrite it this way. The summation of yi over I equals A0 times the summation of 1 over I plus A1 summation of x sub I. That's just taking the A terms and moving them over, and then pulling out those constant factors of A0 and A1. These terms in brackets are all knowable in a measurement. Right? You know what your y's are, because those are the measured values. You know what your x's are, because those are your independent variables. And then 1, you know that one too. I'm telling you it's 1. So it's easy. So now let's switch. We're halfway there. So we've got, we don't have a good way of solving for A0 and A1 yet, but we have at least one equation that relates to them. So now let's do the same thing for A1. Derivative of chi squared with respect to A1 is going to be summation of I of that. Same thing, just now with respect to A1. So what is the derivative of that term in brackets with respect to A1? I'll let you ponder that and finish writing at the same time. Okay, go for it.
Well, according to the chain rule, which you refreshed, it should be 2 times the thing, which is the thing in brackets,
Mm-hmm.
multiplied by negative xi.
Correct. So this is going to be summation over I.
Two times that, right?
2 times that times negative x sub I. I'm going to pull out that factor of negative 2 because this whole thing again is equal to 0, just like I did before. And this will be negative 2 summation over I of xi yi minus a0 xi minus a1 xi squared equals 0. Goodbye, negative 2. On to the next sheet. So if I take this expression and I'm going to do the same thing I did before, group these things over in terms of the summation that includes y, keep that on the left, and put all the things that are dependent on a0 and a1 over on the right. And what we'll end up with is that. I think there's a way for me to select this, right? No. Come on. Okay. Let's go back. Well, I'm going to need some more sheets here, aren't I? There. I'll skip my Java update for now. It won't let me erase that anymore. It's there for good. Sorry about that. All right. So this is one set of equations. You will recall, I'm going to write it up here again, that we had the other equation that looked like this, summation over I of yi from a0, taking the derivative with respect to a0, so these are the two equations with two unknowns. So using these two equations with two unknowns, we can solve for the most probable values of a0 and a1. What's a convenient way of setting up two sets of linear equations? Linear algebra. So we're going to write this as ain't math awesome? A question?
It's a little like slant.
The little slanty thing? That's just to indicate that I'm doing something different over here. It's not part of the same equation. But really it is. This is beta equals alpha times A. So how do I solve for A there? I'm sorry? Oh, you're even more Johnny on the spot than I was thinking. The simple answer, you gave the next step. How do you actually mechanically do it? The simple answer is that you left multiply both sides by alpha inverse. And use the determinant in order to do that. So we have beta equals alpha A. Alpha negative 1 times beta equals alpha negative 1 times alpha times A equals A. And how do you get the determinant, or how do you get the alpha inverse of a 2 by 2 matrix? Alpha negative 1 for a 2 by 2 is 1 over the determinant. Ooh, I think I hope I get this right. Alpha 1, 1, negative alpha 0, 1, negative alpha 1, 0, and alpha 0, 0. I believe that's correct. I could be wrong, but Wikipedia will definitely have the right answer. So we'll put here, double check. The good news is MathCAD does perfectly fine with alpha inverse too, so you don't have to actually know what goes on behind the hood, underneath the hood on that. So
What's the for the matrix underneath the
here,
fraction? Yeah.
that is the determinant of alpha. Again, really that's just the mechanics of how you actually calculate the inverse of alpha, but the bottom line is you just take the inverse of whatever your alpha matrix is, and that allows you to isolate your A's. Okay. What next? Let's keep forging on. How about that? What if your variance What if your variance is dependent on x sub I? I'm going to give you two classic examples. One of them, actually, they're both in the lecture notes as well. One is a measurement on an oscilloscope. How many of you have used an oscilloscope? How many of you have seen an oscilloscope being used by others? Excellent. It's an indispensable tool for those of us involved in measurement science. So in an oscilloscope, you have a trace, and if your peak goes above, if you have some voltage transient, for example, that you're trying to monitor, and this is your voltage range, and oops, wow, that zoomed in on me in a weird way. This is your voltage range, and you might have some peak that does that. How many of you have seen something like that who've used an oscilloscope, right? What do you do when that happens? You turn the knob, right? And what does the knob do? Yeah, it rescales your vertical axis. How do you then compare measurements made under two different vertical scalings? Well, I guess the more subtle question is, what do you do about the variance in each of those two measurements? Because you're fine in tracking the mean value, but you're going to have a different standard deviation in your measurement because of the different noise floor and the different rescalings under those two different conditions. So if you're pooling data from multiple rescalings, you're going to have a different variance depending on which section of data you're talking about. Does that make sense? Okay, so you might have, if you're looking at your values, they might be doing something like that, but you had to switch right there such that the standard deviation here is much smaller than the standard deviation there because you've rescaled, for example. So if you've got this difference in scaling, how do you then keep track of that? This would be one case where you can't just set sigma being a constant and pull it out. You actually need to bear in mind what sigma is in the evaluation of chi-squared and the optimization thereof. Another classic example is curve-fitting Poisson-distributed numbers. If you're doing a linear fit of counts, what's sigma? Sigma squared is mu. Close enough. A factor of 2 and a sign, I think, is always forgivable among friends. I'm sorry? Yeah. So the variance is equal to the mean for Poisson distributed data. What's the implication of that? Well, it means that I'm going to have a very small variance here and a very large variance there, and it will scale with the value itself. So I can't use one value of sigma for all of the data because that would be wrong. Thank you. At least someone appreciated that. So what do we do about these two scenarios? We have to just basically redo the entire math with sigma. I'm not going to force you to do that. I'm just going to show you what the final outcome is, and then let's look at it and see if we could have guessed that to be the outcome from first principles. So in this event where you've got data that have if sigma is not constant but depends on x, then your matrix has sigma in every one of the terms, sigma squared. Oh, actually, this should just have x, or y. And then this one has x sub I, y sub I, over sigma I squared. Stated without proof. The full proof is in the lecture notes, so you're welcome to peruse that if you need to, but yeah, leave it at that. Keep going? Excellent. I just know I'm going to need more of these. What about this equation? Y equals A0 plus A1x cubed. Is this a linear equation? How many say yes? Other than Max. The answer is yes and no. It's nonlinear in x, but it is linear in both A0 and A1. You see that? So in this case, in terms of what we will be discussing, this is in fact a linear equation in the parameters of interest. This is linear. And in fact, we can write this more generally. Any y sub I could be A0 times phi 0 of x plus A1 phi 1 of x. Right, this is also a linear equation. So if phi is a Gaussian function, this is still a linear equation in phi, or in alpha 0. As long as I'm just rescaling a Gaussian function. Okay. So what would you, let's explore this one here. What would be your guess as to how our expression here would change if I had x cubed instead of x?
X cubed instead of x.
Yeah. Oh, everywhere you see an x, put an x cubed.
Yeah.
So this would be cubed. This would be cubed, cubed, and to the 6th. Yeah. That's easy, right? What about, let's throw another one at you here then. How about y sub I equals a0 x sub I plus a1 x squared of I? What do you think this does then? Yeah.
Replace xi with xi plus x squared, or xi squared.
Nope.
Okay.
We got this 1. If we look back, think about where did that 1 come from in the first place? It came from the derivative with respect to a0. Right? So with this 1 is going to be replaced by x, because that is now the term in front of a0. And then this 1 in front of a1 will now be replaced by x squared. So what will happen in this term, you're going to have actually x here, x times x squared here. So this will be x cubed. And then x squared squared. All right, the pattern might not yet be perfectly clear, but I think it will be if we explicitly, if we go back to the very general equation. No, let's forget about the summation and just assume we have 2 terms again, where phi is any function of x. Now here's where things get a little dicey, because we have lots of different functions of x all happening at the same time, right? We have y, which is a function of x. We've got phi, which is a function of x. And then we have f of x, which is the PDF in x. Or in y, f of y, which is a PDF of y. So here's where your head just about explodes after a night of 621 exam writing, right? And so I'll probably pick this up and review this again at the start of next lecture. But I'm just going to put up here what the final result is to plant the seed. How about that? The general expression, we forgot one other place we have to change things. We have to put an x sub I here and an x cubed here. X squared there. So it shows up both places. So the general equation, for the general equation, a general linear case of y sub I equals a0 phi of x sub I plus a1 phi 1 x sub I. This is the general case. It will turn out that our beta is going to be the summation of I. We'll leave in sigma 2, so you've got everything at your disposal here. It's going to be phi 0 x sub I times y sub I over sigma I squared. And then this will be phi 1 x sub I y sub I over sigma I squared. And what does alpha look like? I'm going to run out of room, but that's okay. Actually, row column, this will be the 0, this should be 1, and this should be 0. Okay. So it's a lot of writing here. I'll let you fill that in.
What's that at the very end, A, not in?
Yeah, I ran out of room. That's A0 and A1. That's a vector. Oh. Beta equals alpha times A. So that's just the form of alpha. And I just want to be clear on what all the functions are, and then I'll answer your question. Y are the data, right? These are the measured values, and they are distributed according to a normal PDF. The assumption behind all of this is that the data are normally distributed, so f of y is normal. That's the first function that we have to contend with, actually the second, because y is a function of x. And then we've got a distribution in y that's given by a PDF that's not shown here. And phi is another function of x. And here's, the first time I saw this, I was just lost. So I'm anticipating the same thing for you as well. But I think if you relate it back to the explicit expressions like shown here, where in this case, phi 0 is 1, and phi 1 is x cubed. That's what we mean by a function of x. Then hopefully it's a little more concrete in terms of what we mean by phi. And then we can invert alpha to solve for a, just like we could before. And that is a good stopping place, I think, for now. So on the agenda for Tuesday is, first of all, a good night's sleep, followed by some programming and some questions on the linear fitting topics that were covered today. And then we'll jump into nonlinear curve fitting and approximations thereof shortly afterwards. All right. Congratulations on completing the first third of the course.